Good day, everyone. I'm Joanne Espiliaga, and we are going to talk about the topic on non-Euclidean geometry. Before we proceed on non-Euclidean geometry, let's talk about the foundation of geometry and Euclidean geometry first to know how and why non-Euclidean geometry was discovered. So, geometry derives from two Greek words. The first one is geo, which means earth, and metron, which means measure. Geometry literally means to measure Earth. In mathematics, geometry is the study of shapes, sizes, locations, and spatial characteristics. It uses figures, angles, planes, lines, and points to analyze and characterize real-world objects and patterns. Now, let's proceed to the next, the Euclidean geometry. Do you know who the father of geometry is? Yes, it's Euclid. So, Euclid is an ancient Greek mathematician, and he flourished in Alexandria in 300 before Christ era. Also, he founded the School of Alexandria. He is known for his contributions to geometry with his book Elements in 325 before Christ era. The Elements contain 13 books which outlines the fundamental principles in geometry. It includes the concept that planes are flat and has infinite surfaces. Lines extend indefinitely in both directions, and parallel lines that are graded in a plane make it look like a graph paper. Euclid based his element from different works of earlier mathematicians. Another contribution of Euclid is that he developed the five fundamental postulates in geometry, which we are going to talk about in the next slides. These contributions of Euclid made him to be often called as the father of geometry. Now, let's proceed to Euclid's five postulates. Postulate number one states that one and only one straight line can be drawn through any 2 points. As we can see in the figure below, there is point A and point B, which serves as our 2 points. This postulate states that we can only draw one line segment from point A to point B, and no other line segment can also be drawn that makes the 2 points be connected. Next is the second postulate. Postulate number 2 states that a line segment can be extended in either direction indefinitely. So we already have a line segment that connects point A and point B in postulate 1. In postulate 2, on the other hand, as we can see in the figure, both ends of the line segment were extended, which can be infinitely extended in opposite directions. Now, let's proceed to the other postulates, which will be discussed by Shallow PC Long.
Now, let's proceed to the postulate 3. So it states here that a circle can be drawn within the center and radius. So it states that through one segment, we can draw a circle at any point and radius. And postulate 4 states that all right angles have the same measurement or measure. So all angles that measure 90 degrees are all congruent. And lastly, postulate 5. Through a given point, not on a given line, one and only one line can be drawn parallel to a given line. So if we draw one line with a point that is not on the given line, then we can form a line that is parallel to the given line. So far, all of these postulates that was based on points, lines, and planes. However, the fifth postulate of Euclid is not yet clear, which results in confusion, and some consider that it still has to be proven. Therefore, it is not a postulate, rather it should be a theorem. And what is the problem with the fifth postulate? So for the past 20,000 years, mathematicians are not satisfied with the fifth postulate, leading them in using Euclid's first four postulates in trying to prove it, which was called the fifth postulate problem. So mathematicians didn't succeed in proving the fifth postulate without introducing new postulates, where the concept of parallel lines are different from Euclid's. So, together with the emergence of new postulates, a new geometry was also emerged. It is called non-Euclidean geometry. As the name suggests, this geometry is the opposing geometry of Euclidean geometry, specifically the fifth postulate. It exists because of the discovery of mathematicians that the fifth postulate of Euclid is not always true in every situation. So, some mathematicians that tried to prove it were Ferdinand Carl Schwarzschild and Carl Friedrich Gauss. However, they failed to publish it. So, under non-Euclidean geometry, there are two types. First, the elliptic geometry, and second, the hyperbolic geometry. So let's proceed first to the elliptic geometry, or also known as spherical geometry. It is described as a geometry of a surface that with constant positive curvature, like the surface of a sphere. And it was introduced by Bernard Riemann in 1854. So it's also elliptic geometry is also called Riemannian geometry. So elliptic geometry, it is a circle of elliptic space is defined as usual. The set of all points is a given distance from a point. Given a line and a point, no parallel lines to the given line can be drawn through that point. So compared to Euclidean geometry, there are two principles here, which is number one, planes are shaped like spheres, which is finite in area, and number two, lines are great circles and finite in length. So, compared to Euclidean geometry, spherical geometry is a system of points, great circles, and a sphere. It is based on the astronomy of the Earth and the need to measure time accurately. So based on the principles that I have mentioned a while back, wherein in lines, it's always gonna be a great circle. Because if we draw a line from one point, compared to Euclidean geometry, elliptic geometry argues that there is no parallel line in a sphere. So we can see in the slide that if we draw two lines which are great circles on a sphere, they will always intersect with each other. So forming of parallel lines are not possible. In Euclidean geometry, the sum of all the interior angles is equal to 180 degrees, and forming of one right angle and one obtuse angle is only possible. However, if we draw a triangle on the surface of a sphere, we can see here that it can form more than one right angle or more than one obtuse angles. So let's take a look at the picture on the slide. We can see here that the triangle on a sphere, and it formed two right angles and one obtuse angle. So if we add them all, then it will the sum will be more than 180 degrees. Let's proceed to the application of elliptic geometry. So where can we apply elliptic geometry? We can use this kind of geometry in various fields, such as architecture, biology, cosmology, and also physics. In elliptic or spherical geometry, it always remember that there are no parallel lines, and any two lines would intersect in two places. And the sum of the interior angles of the triangle will add up to more than 180 degrees but less than 540 degrees. So those are the things that we should or we need to um, always remember in elliptic geometry.
The next type of non-Euclidean geometry is the hyperbolic geometry. Hyperbolic has the root word meaning excessive and exaggerated. It is based on planes that are negatively curved and it contains more of the warps, bends, and frills that are symptomatic of this space. Hyperbolic geometry has the concept of hyperbolic planes, which is the fundamental surface where this type of geometry happens. The planes on hyperbolic geometries are negatively curved or bends. Just imagine a Pringle chip. The surface, the surface of the chip is not a flat surface, but rather curved. That can be an example of hyperbolic space. Now let's proceed to talk about one of the prominent figure in hyperbolic geometry. So we have here Janus Bolyai, an Hungarian mathematician and one of the individuals who discovered hyperbolic geometry. He, along with other mathematicians, discovered and proved that hyperbolic geometry is valid and consistent system, even though it does not satisfy the fifth postulate of Euclid. So, we already know that non-Euclidean geometries, including hyperbolic geometry, does not satisfy the fifth postulate of Euclid. But hyperbolic geometry satisfies the postulate 5b. So, what is postulate 5b? Postulate 5b states that through a given point, not on its given line, many different lines can be drawn parallel to a given line. This postulate is one of the alternative postulates that mathematicians discovered after the unsuccessful proving of Euclid's fifth postulate without introducing new postulates. Hyperbolic space, as we can see on the figure, satisfies postulate 5b because of all the Freely waves of the space through which a line can travel. There is more than one line through point P that will never cross line segment AB. Here is another representation of hyperbolic geometry. It states here that given a geodesic and a white point not on it, there are infinitely many geodesics through the white point not intersecting the first geodesic. The geodesics that are mentioned in the representation is equivalent of straight lines in the hyperbolic geometry. Those are the shortest paths between two points. So next, the largest triangle on hyperbolic space has an angle sum of almost zero. Planes are negatively curved and infinite in area, and lines are infinite in length. So we all know that in Euclidean geometry, the angles of a triangle always add up to 180 degrees. But in hyperbolic geometry, the angles of a triangle only add up to less than 180 degrees. This means that the larger the triangle is, the closer the sum of its angles gets to zero. So after our discussions on hyperbolic geometry, do you already have an idea where we can use hyperbolic geometry? Can you give some real life application of it? If no, here are some applications of hyperbolic geometry. This includes gravity and special relativity, computer graphics and visualizations, physics and cosmology, architecture and urban planning, art and design, and mathematics, education, and research. So to summarize the difference between Euclidean geometry and non-Euclidean geometry, let's take a look on this table. So as we can see in the table, in Euclidean geometry, the plane has a flat surface and the triangle that can be formed in it is always equal to 180 degrees. On the other hand, in the spherical or elliptical geometry, the plane has a spherical surface and the triangles in this geometry is always greater than 180 degrees. And lastly, in the hyperbolic geometry, the plane has a curvature surface, making the angles of the triangles in it always add up to less than 180 degrees. And that's the end of our discussion on non-Euclidean geometry. Are there any questions or violent reactions? If none, here's a video about non-Euclidean geometry for us to watch to further understand non-Euclidean geometry. Thank you!
Euclidean and non-Euclidean geometry. To understand the theories of the universe and space-time curvature in a better way, we must have an idea about the different types of geometry and about their uses. Euclidean geometry is a mathematical system named after Greek mathematician Euclid. It is described in his textbook of geometry, The Elements. This is the plane geometry, still taught in secondary school. Euclidean geometry is mainly a systematic and logical representation of earlier knowledge of geometry. We all know, according to this geometry, if a straight line and a point not on that line given, then there is only one line you can draw that passes through that point and is parallel to the first line. It is Euclid's parallel postulate. So, you can see this geometry is flat and its curvature is a zero. But the main problem is this geometry defines the situations of the plane only. When we are dealing with different surfaces, we are faced many drawbacks of solving problems through the same geometry. This geometry is also called parabolic geometry. If you try to apply the same geometry on the surface of a football, then you will face problems. But we always need those theorems which can be applied to every situation. We saw that our universe is not so flat, space and time can be curved. So, now we need some better geometry to explain the laws of the universe. Carl Friedrich Gauss and Ferdinand Karl Schweikart had the ideas of non-Euclidean geometry at the beginning of the 19th century. But, they did not publish their thought. Then, in 1830, Janusz Bolyai and Nikolai Ivanovich Lobachevsky separately published treatises on hyperbolic geometry. It is also called Bolyai-Lobachevsky geometry. In this geometry, the surface is negatively curved. This leads to a variation of Euclid's parallel postulate. According to this, for a given straight line and a point not on the line, there exists an infinite number of straight lines through the point parallel to the original line. Then in 1854, Bernhard Riemann founded a special type of geometry, called Riemannian geometry. It discusses the ideas of manifolds, Riemannian metric, and Riemannian curvature. It is also called spherical or elliptical geometry. Here the surface is positively curved. In this geometry, Euclid's parallel postulate has a form like this. For a given straight line and the point not on the line, there are no straight lines through the point parallel to the original line. We know that the sum of angles of a triangle is 180 degrees in Euclidean geometry. We all study it from school. But, it is very interesting that for hyperbolic geometry, The sum of the angles of a triangle is less than 180 degrees, and for Riemannian or elliptical geometry the sum of angles is always greater than 180 degrees. On a sphere, the sum of the angles of a triangle is not equal to 180 degrees. The surface of a sphere is not a Euclidean space, but locally the laws of the Euclidean geometry are good approximations. In a small triangle on the face of the earth, the sum of the angles is very nearly 180 degrees. If you like this short video, then please subscribe to this channel for more interesting content. You can also share this video to your physics lover friends. Thank you.